So yes, now to start with, let's see. Actually, all of you can unmute yourself. Which part of your slides does that start from? Yes, comparator. Okay. 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 So let's start. We can actually start. So when you want to get a parity checker, we can have actually two types of that. The first one, which is even parity generator, and then the parity checker, and then the other one, which is odd. So you have even and then you have odd, right? Now, in sending signals, right, when you are doing data transmission, you would like to maybe detect if there is an error in what you are sending or not. So we design a parity bit generator together with it so that we can use it as a scheme in checking for error and then correcting them, basically. So what you do is you generate the parity and then you append that parity that you've generated with it, with the data that you are going to transmit. Then you send it through the channel. So maybe you could have a transmitter here. And then you have the channel like this, and then you have the receiver here, and that's so you append that parity with it, and then you transfer it through the channel. Now, when it gets to the receiver side, it's the duty of the receiver to use the checker to detect whether there is an error in it or not. So if there's an error, then it uses that mechanism to correct it. If there is no error, then you just receive the signal. That's all. So that's a practical way of thinking about the usage of parity generator and parity checker. Please, is that it? I'm sorry for my background there. So to start with, if you want an even parity checker, what you do is you check the signal that you are sending, right? Let's say a generator. So maybe, let's say at some points, you are sending a 00, a 01, a 10, and then a 11. So what happens is, if you want to append a bit to this for even parity generator, what you do is, let me admit this guy. Okay. So what you do is you append a bit, which is going to be a 0 or a 1. And in that case, since you want even generator, what you would require is that you should have even number of ones in your signal. So if the number of ones is odd, then you say that you are appending, let's say, a 1 to it. If the number of ones is even, then you append a 0. So it means it's like there is no error. If there are even number of ones in it, there's no error. So you append a 0. If it's odd number of ones, then you append the 1 to make it what's even. That's the idea behind this. So in this case, if we are designing it for an even parity generator, it means here you count the number of um ones here, right? If it's even, you append a 0. If it's odd, you append a 1 to make it even. So what you do here is, when you take 0, 0, you realize that this one actually has, if I should say, even number of ones. Basically, you are not seeing any one here. So there is no error in a way. But then this guy has something within it. Or relax. I think I should be asking you guys questions. So if you have this, right? Actually, let's continue. You have 0 here. Here there is an odd number of 1 here because it's a 0 and then a 1. So it means what then you have to do if you are using even parity? You append a 1 to make it even, right? And then here too, you have a 1 and then a 0. So that case, you have an odd number of 1. So you append a 1 for the generator. And then lastly, when you have 1, 1, that one too, you have even number of 1s in the data bits that you are going to transmit. So in that case, you append a 0 to it. So that will be your parity generator part. Then for the parity checker, I said when you are transmitting, you transmit, let's say here is an A, here is a B. So you transmit A and B through the channel, right? When you are doing the transmission, you transmit A and B through the channel, and then what happens at the receiver side is you take in A, B, and then G in a way. So it means at that point in time, you have 3 bits coming to your receiving end. So initially, you were sending 3 bits, actually, you were sending 3 bits, but then your actual message that you were sending was 2 bits. But you append this guy to actually check for error, because when you are transmitting data, let's say you are using a wireless medium, fiber optic, a wireless medium could be like a radio signal. There are lots of errors, disturbances here and there within the channel. So there could be some errors here and there. Could be that you are calling someone, then what you are saying is not reaching the person, right? So there are a lot of practical examples that you can have. When you are traveling, sometimes you hear some radio signals coming into the radio signal that you are on. So maybe you are listening to Onya FM. Let's say you are traveling from Kumasi to Accra. You get some point and then you hear another radio station, maybe Peace FM. There are signals coming into or interfering into your signal that you are listening to. So it means you are listening to Onya, but then you are hearing some of Peace messages inside. So that is interference. So we use these things to actually cater for some errors that could happen in data transmission, right? So you transmit these 3 bits, and then at your receiving end, you will take the 3 bits. So the 3 bits will be, let's say, A, B, and then what's G in a way. Then you generate your parity checker. So your checker too, if it's going to be an even one, you check if there is an even number of ones in the data that you've received, then you append a 0 in this case. If there is odd number of ones in the message that you received, then you append what? A 1 to make it even. So it means you are correcting the error. That wasn't what you were supposed to receive in a way. So that's the whole idea about parity generator and checker. So now I'll move on into doing 3 bits with you. Actually, if we do 2 bits, you'll see that 2 bits will align with 3 bits. 3 bits will align with 4 bits. 4 bits will align with 5 bits. It doesn't matter on the number of bits that you have. You will still end up getting the same logic, because these 2 bits that I've done here, if you take A and then B and then G, right? Your output G that we have here, right? Taking these 2 inputs is going to be this place, because we are using min terms. I hope you get it. We are using min terms. So we look at where the output is having a 1. Exactly. I want to hear from you guys. So in this case, it means when you have a 0 and then a 1, you are getting a high. When you have a 1 and then a 0, you are still getting a high. So it means your generator would be written as A bar B, right? Or A B bar. And then whenever you have 0, 1, and then 1, 0 giving you a high, you should know that it's an XOR, basically. So here, when you check this, is G equals A XOR B, which I think you know now. So it means your generator is actually what? A XOR B. So it means if I tell you to design a generator for a 2-bit data transmission, you are supposed to end up with an XOR gate of the 2 inputs, basically. And then as your receiving end, so here we are doing 2 bits, even generator. Now this is the generator that we are having. Now let's try and do the, how do we call it? The checker. So at the receiving side, I was saying that you will have 3 things coming there because at that point you sent in A, you sent in B, and then you also sent in the G, right? So the G was appended to the signal that you were sending to check and then correct errors, basically. So let's do or draw a table for the parity checker. Okay, so I'll leave the generator formula or equation there. So let's do the checker. So here is the checker that we are going to make. So with the checker, the inputs that will be coming to the receiver would actually be 3 inputs. The 3 inputs will be A, B, and then G. So let me put P here as your parity checker. And then whenever you have 3 inputs, you know that it's going to be what? 2 to the power what? 3. So it means you have 8 possibilities. Now the 8 possibilities, he taught you that to make it simpler for you, all you have to do is here is 2 to the power 0, right? 2 to the power 0. So it means after every 1 bit, flip. So you have 0, 1, 0, 1, 0, 1, 0, 1 all along. Here is 2 to the power 1. So you have 2 bits, then you flip. So maybe you go from 0, 0, then you flip to 1, 1, right? Then another 0, 0, you flip to 1, 1. And then here too, you have 2 to the power 2, making what? 4 bits. So it means after every 4 bits, you have to flip. So you put 4 zeros, then you flip to 4 ones. So that's how we are going to fill this table, which I think you know already. I don't want to assume actually. So I'll do everything. So here you have 0, 1, 0, 1. There's 4. 0, 1, another 0, 1, like that. Let me draw my lines so that I can see them well. Okay. Sure. It's looking some way, but we'll manage. So here is 0, 0, 1, 1, 0, 0, 1, 1, right? And then here you have 0, 0, 0, 0, 1, 1, 1, 1, like this. So this will be my table. Now, what will be my checker? So for my parity checker, since we did even, right? Let's do even parity checker here too and see what happens. So, okay. So with the even parity checker too, we'll count odd number of ones, which will append a 1 to correct it in a way. And then if it's even number of ones, we append a 0. It means there's no error. That's the whole idea here. So here you have 0, 0, 0. So you append a 0. You have 0, 0, 1. It means you have odd number of ones here. So you append a 1 to make it even. It means you are going to correct something here. You have a 0, 1, 0. You append a 1 because the number of ones is odd in a way. It's just 1. Here you have 2 ones here. 0, 1, 1. So it means you have to append a 0, right? Then here you have 1, 0, 0. So it means you have odd number of ones. You append a 1. You have 1, 0, 1 here. So it means even number of ones. You append a 0. And then here you have 1, 1, 0. So even number of ones, you append with a 0. And then here you have 1, 1, 1. Odd number of ones, you append with a 1. Exactly. Before we continue, I want to hear from you guys. So, okay. Okay. Can you still see my screen?
No, please.
Okay, I think it went. Okay, so let me reduce this normal. Okay, so let's continue. So here, since we have 3 inputs, I don't want to be writing all the expressions one by one. So let's use K-map here. So using K-map and then knowing that we have 3 inputs, it means we are supposed to end up with 8 outputs. So our table will look like this. And then we'll have A here, we'll have B, and then what's the G here. So this is our P that we are looking for. And then here, it's like using gray code. Gray code is the next bit should be changing. Sorry, yeah, the next stage, let me use stage, should change in just 1 bit. So here is 0, 0. You can go to 0, 1. It has changed in just 1 bit. You can go to 1, 1. It has changed in 1 bit. And then 1, 0 here. It has also changed in 1 bit here. So now we'll use the output here, which is P, to fill the table. Now the first 4 is up to this point. That is giving us 0, 1, 1, 0, right? So 0, 1, 1, 0 means is here, 1 is here, the next one is here, and then the 0 is here, because here is 3, 1, 1. And then when we come to the last 4, 2, here we have 1, 0, 0, 1. So we fill it like this, 1, 0. Then go to the ending side, 0, and then 1. Now, I think Dr. Poku told you this. If you have something looking like this, and then the first bit is 0, but then you have 1, 0, 1, and then 1, 0, 1, 0. It's like you can't actually group any 2 of them together. They have been isolated. And then since it's starting from 0, it actually looks like an XOR gate. So you have this, you have this, you have this, and then you have this. If we are supposed to write the expressions one by one, you still end up with XORing of the 3 inputs. So it means P here is basically A XOR B XOR with G. That's all. Please, is that clear? So another thing to note here is that after designing your generator and then your checker, what the question would demand you to do is to just draw. So actually, what you had in your exam was just for you to draw, because by then you wouldn't have that time to be thinking of drawing a table and then now coming to minimize and then get your output expression. No, time will not be on your side. So you just have to know it off head. So in this case, knowing it, hey, I didn't even ask you, can I clean it? Let me see. Can I clean? Can I clean, please? Okay, sure. If you have challenges, you have to alert me as I'm moving ahead, right? If you have challenges. Because here, shouldn't be like you didn't want to speak up. No, it wouldn't help us. Not at all. So here, if it means that if I want to draw for a parity generator with 2 inputs, A and then B, I'll just have an XOR like this, right? And then this will be my generator. Now, if I want to design the parity checker, I can tap, because here was A XOR B, I'll have something like this. This will be my generator. Now for the parity checker is A XOR B XOR with G. So it means I can tap from this input and tap from this input as well, and tap from this input also. if the question demands you to use just 2 inputs XOR gates, so let's say 2 inputs XOR gates, it means that I have to place an XOR here first to get this first part of it, this first XOR. Then what do? I have to XOR it with G, but G is only one term. And I'm supposed to design with what? 2 inputs XOR gates here. What you do is you hardwire another signal like this to make it 2 inputs. So it's like G is here and then G is here. So in a way, it's just 1 input, but then you are connecting a short wire. Let me use a short wire in this case. So you are connecting a short wire to it to make it 2 inputs, but it's the same signal. So when G XORs G, all you get the same thing, right? Basically, you get the same thing. So it's like 1 XOR 1 is what? 0. How do we call it? This is 0, basically. But then basically this hardwiring 2 inputs to get the output back. So in a way, you still end up getting by one way or the other. So here you just hardwire this with another XOR. Then now you connect all of them to another XOR to get your output expression. So if the question doesn't demand you to, I'm coming. Okay. So you connect this output to another XOR gate, then that will be your P. That's all. But if the question doesn't demand you to use a 2 input XOR, then what you can do is you can make the XOR gates just 3 inputs. So you can tap from here, and then tap from B, and then make it a 3 input XOR gate to get your parity checker. That's all. So this is your 2 inputs generator and then your checker. Now, the one who was going to ask a question, you can talk. You can unmute and talk. Hello. Hello. The person who wanted to talk, you can talk. But is this making sense? I want to hear from you guys. Is this making sense? Okay, can I clean this so that we can continue? Okay, sure. So basically, in an exam, even if the bits are 5, you still get an XOR gate. Just put that in your mind. So let's say we are designing for 3 inputs parity generator. It means we have 3 inputs which are A, B, and then C like this. Then we have to design for this, a generator for this first. It means your checker will be 4 inputs because here, these 3 inputs will be appended with the G to be transmitted through the channel. Then as you're receiving end, you use the parity checker to detect and then correct the error in your system. So let's say we are designing an even one. Let's do this for you to see. So here too, I have 0, 1, 0, 1, 0, 1, 0, 1. I have this. Okay. Now let's see. 0, 0, 1, 1, 0, 0, 1, 1. And then I have 1, 2, 3, 4, 1, 2, 3, 4 like this. Okay. So now the generator that we are going to get, we are still doing even, right? We are still doing even generator here. So here I have 3 zeros, so I'll append a 0. There is no error, basically. I have a 1, 1. So I have to append a 1 to make it even. I have a 1, 1 here too. So I have to append a 1 to make it even. Here I have 2 1s, so they are even number of 1s. I have to append a 0 because there's no error. Now here I have 1 1, so I will append a 1 to make it even. 1 0 1 2 have 2 1s, so append a 0 because they are even number of 1s. Here too you have 1 1 0, so I'll append a 0. And here I have 3 number of 1s, which is odd. So I have to append a 1 to make it even. So basically, this is the parity generator for a 3-bit input, right? Yes, a generator for a 3-bit input. So here, to make things simple for us, let's draw the key map for the generator. So the generator, let me reduce this. I'm coming in. So for the generator, you have something like this. 1, 2, 3, 4. Okay. Now we have A here, we have B, C, right? And this is the generator that we want. So here is 0, 0, 0, 1, 1, 1, and then 1, 0. Now I have a 0 and then a 1 here. So here too, when I take the first 4, the first 4 is here. I have 0, 1, 1, 0. So I place them here, 0, 1, 1, 0. Then the last 4 will be what? 1, 0, 0, 1. So 1, 0, 0, 1. So this is just looking like an XOR because here, 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 and then it's starting from a 0. So whenever you have something like this, it's just an XOR. So here you have what? A XOR B XOR C, giving you G. That's your generator, basically. Yeah, that. So you could clearly see that when we did for a 2-bit, it was an XOR between the two. When we did for 3-bit 2, it's still an XOR for the 3. If we are supposed to do the checker, right, we'll have 4 inputs. It means we are going to have 16 outputs to minimize. That would mean we have to redraw this table. So this is just going to be the generator. So the checker, have to make it very small. Can I clean this? Can I clean this? Okay. So I'm going to clean this. Okay. So can I even draw this whole 16 here? That's the issue. So this is our P. So here will be 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Interesting. 0, 1, 2, 4, 6, 8, 10, 12, 14. Okay, I should append another 0 here and then a 1 at the bottom. It wouldn't go there, so let's continue like that. So the last bit is actually a 1, basically. Let's see. You will fill it. You'll see what will happen. Yes. Oh. Okay. So this. Okay. So here 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, and then the last one here, down here. if I can do this. So 1, 2, 3, 4. 1, 2, 3, 4. Another 1, 2, 3, and then the last one. So here 2. 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8 like this. Now let's see the output that we'll get for the parity checker. So here too, we are still doing for even, right? For even. Now with this, here too, we have even number of zeros here. There is no 1 here, basically. So here P becomes a 0 because there is no odd number of 1s here. Now here you have 1, 1. So it means you have a 1. Here you have 1 1s, you have a 1. Here you have 2 1s, you append a 0. Here you have odd number of 1s, you append a 1. Here is 2, so a 0. Here is 2, a 0. Here is 3, so a 1. Here is just 1, so a 1. Here is 2, so a 0. Here is 2, so another 0. Here is 3, so a 1. Here is 2, so a 0. Here is 3, so a 1. Here is actually 3, so another 1. And then here is 1, 1, 1. I think another 1, so maybe a 0 like this, right? Basically. Now, it means we are supposed to draw a 16K map or a 4-input K map anyway. Let me say 4-input K, that will be precise. So it means we will end up getting something like this. Okay, now let's do this. So you have A, B here. You have 0, 0, 0, 1, 1, 1, and then 1, 0 here. And then you have C, G, right? That's the movement. So P is what we are doing here. So here too, you have a 0, 0, 0, 1, a 1, 1, and then a 1, 0, right? So what this means is, let's look at this output that we are getting. The first 4 is 0, 0, 1, 1, 0. Let me change to red. So let's fill 0, 1, 1, and then 0. The next 4 is 1, 0, 0, 1. So 1, 0, 0, 1, like this. Now the next 4 is 1, 0, 0, 1 again. But the next 4 should come here because here is 2, here is 3. So here will end it. So you should come here and then place your 1, 0, 0, 1 here, right? Then the last 4 becomes 0, 1, 1, 0, which will be placed here, meaning we have 0, 1, 1, and then 0. Now let's see. Here too, you have here, here. Let me change the marker to blue. So here, oh, what is this? I'm coming. Okay. So you have this, you have that, you have this here, you have this here, you have this here, and then you have this here. So it means we can't really join any of them, right? The way they are looking like. So it's still an XOR, basically, since it's starting with a 0. So it means the parity checker here too is going to be A XOR B XOR C XOR what? G, your generator. So it means it's still just XORing the inputs that will be coming to the receiver. So in a way, this will be at your receiving end. It's supposed to detect error and correct it. So when it detects that there is an error, there is odd number of 1s in your signal, then it will append a 1 to correct it. Basically, that's the work of it. So that's basically how we use this in our transmission systems. I think it has come out clearly, right? For you guys. I need a yeah from you guys, if it's okay. You can unmute and then talk. If you have challenges, you can let me know. Any challenge?
Hello?
Yeah.
Yeah, someone asked a question in the comments comment
Yeah.
box or something, and you
Oh,
haven't
okay.
addressed him yet.
Oh, sorry. So let me see the chats. Yeah. Yeah, actually, what he was saying was true. Yeah. Let me see. So yeah, actually, G X or G, yeah, in a way. It's supposed to be so let me address that here. Where is it? Okay. Oh, I'm coming in. Okay, sure. So the question that the person was saying, yes, let me address it here. Where is my marker? Here. I'm coming. Okay, sure. So let me address it here. Okay. So let me clean this part. So actually, yes, of course. I didn't really talk about that. It's supposed to be when you are hardwiring the two, since G XOR G is going to give us a 0, it should be a 1 and then a 0 to give you a 1 in a way. So if you want G bar, all you have to do is to XOR with G bar instead. Then you get G, right, in a way. So you get a high. So it means G here will determine the output that will be here. Do you get it? So when you are hardwiring for a 2 inputs, you should do it this way instead, actually. So yeah, I think your question has been answered. When I was using the 2 inputs, yeah, exactly. So with an XOR, you should have changing bits, a 1 and then a 0 to get a high. So if you want G at the output, then it means you have to do G XOR G bar to get the output as G. So yeah, he's right. So basically, what we've noticed here is that whether you have 2 inputs, how do we call it? 2 inputs generator or parity checker, 3 inputs in that case. If you have 2 bits to transmit, you have the generator having just 2, like A XOR B. And then you have the parity having 3 inputs. The 3 inputs, I said A will be coming with B and then to be coming with the generator. So you append the generator with it. So it's like P is equal to F of A, B, and then G in this case. And then G is actually a function of what's A and B like this. And then here is A XOR B. And then here you will get what? A XOR B XOR what? G. And then we've realized that if you have 3 bits inputs, then your generator will be having 3 inputs like A, B, C, which is A XOR B XOR what? C. XOR C. And then your parity will be having A, B, C, and then your generator together with it for the error detection and correction. So here you have what? A XOR B XOR C XOR what? G. So this was for even. Now, I won't do the odd one because it's just like the even, just that with the odd, when they tell you odd. So I think in your midterm, someone showed me your question and then I saw that it was odd checker, basically. So if it's odd, it reverses, the process just reverses. That's all. So that one, you'll be counting the odd number of ones in it. If it's odd number of ones, then it's, how do you call it? It's a 0. You are going to append a 0. It means there is no error. But if it's even number of ones, then you append a 1. So in that case, let me just do a 2 inputs bit parity generator and checker for it, for the odd one. And then if you go to higher levels like 3 bits, 4 bits, 5 bits, you still end up getting the same thing. Nothing will change, just like how we did for the even. So let's say odd, we are doing 2 bits inputs. So the 2 inputs, let's say we have A and B. 0, 0, 0, 1, 1, 0, and then 1, 1. Like this. Now, if you have 0, 0, we are saying it should be odd number of ones. So if you have 0, 0, it's not odd. So you have to append a 1 to make it odd. That's what it means. So here we append a 1. If it's 0, 0, 1, then it's odd. That's what we want. So it means there is no error. Append a 0 in that case. If it's 1, 0, the same thing. Odd number of ones, you append with a 1. And then here is 1, 1. Sorry, here is 0. Sorry. Then here we have 1, 1. It's even number of ones. So append with a 1 to make it odd. So here, when you even draw a 2 inputs schema for it, it's just basic here, because here, when it's 0, 0, the same bit is giving you a high. When it's the same bit, giving you a high. Changing bits is giving you a 0. And then in digital systems, you know that if the bits are changing, and then it gives you a 0, and then the bits are the same, it's giving you a high, it's an X no. So here it's going to be A X no B. So it's like this with the not at the end. So this will be your generator, like that. So here you end up getting 1, 0, 0, 1, like this. So here and then here. So it means you have X no. It will be the same for the parity checker. That one too, when you do the 3 inputs A, B, G, giving you P, you end up getting an X no. Let's just show that briefly. And then I think that will be that for this section. Then we can move on to the others and all that. So A, B, G, and then P, like this. So here, 0, 1, 0, 1, 0, 1, 0, 1, like this. 0, 0, 1, 1, 0, 0, 1, 1. 1, 2, 3, 4, 1, 2, 3, 4. So here too, let's see what we'll end up getting as our P. So the P here, you have 3 zeros. It's odd that we are looking for. So if you have 3 zeros, there is no odd number of 1 here. So we have to append a 1 to correct it. So it means when you were receiving the signal, right, there were 3 bits zeros or zeros. So you have to append a 1 to correct that error in the signal. You are supposed to receive a signal which has an odd number of 1. That's the meaning. So here, 0, 0, 1 means you have an odd, so it should be a 0. 0, 1, 0 should be what? A 0. 1, 1 means even, you should append a 1 to make it odd. Here, it's an odd already, so 0. Here too, even. So yeah, you have to append a 1. Here is even, you have to append a 1. And here is odd, so you have to append a 0. So now let's draw the 3 input schema and see. Yeah, 3 input schema. Okay, so you have A, B, G, and then P like this. So this came up. Let's fill the first 4 is here. 1, 0, 0, 1. So 1, 0, 0, and then a 1. The last 4 is also saying 0, 1, 1, 0. So 0, 1, 1, 0. So here too, you can clearly see that you have this this, and then this. And then 1 is actually starting. So if 1 is starting, and then you can't join 2 together, you have just 1, 1, 1, 1. You can just form groups of 2 to the power zeros, like ones in a way. Ones of ones, and then 1 is starting. It should tell you that you have an XNOR gate. So here P becomes what? A, XNOR B, XNOR C, like this, basically. So this is it. So this should tell you that whenever you have an even parity generating in the checker, you just be having XOR gates. That's all. And then whenever you are having an odd parity generating in the checker, you'll be having XNOR gates, basically. So in an exam, he doesn't demand you to draw this, right? He doesn't demand you to draw this. You should just know it off head. You should know this off head. So in your exam, I think there was a question like that. So all you had to do was to just draw an XNOR gate of the inputs that he was requesting for. So if it's 5 inputs that he's requesting for, the generator, you know that it will be 5 inputs, but then he told you to use 2 inputs X NOR gates, right? And then maybe another NOT gate, right? X NOR and then NOR gates. So you have this, maybe the first 2 signals, right? Let's say A and B. And then this, you have C and then D like this too. Sorry, there should be a note here because your question was actually odd parity. So you have this. Now the last one, so this can go and then combine with another XNOR. So you have this. Now it's left with the last guy. So the last guy will come, but its other guy will be noted like this. Then you hardwire it into this. You XNOR first. Then the output of these 2 guys will also be what? XNOR together to get the generator like this. Then now, if you want the parity checker, it's all these inputs plus the G, then you XNOR them together. So you draw that circuit to addition. Then you are done with the question. That's all. So he just wanted you to know it offhand. If you've done a parity generator and then a checker before, you should know that even is XOR and then all this XNOR. So just keep that at the back of your mind, right? That's all. So can we proceed to the how far this? I think that's what you guys said. Can we proceed? I want to see a lot of reactions so that I can know if I should proceed or not. Okay. So now it's coming out clearly, right? Sure. So since you guys are saying we should continue, then I think I can do so. So let's start with the how father first. Now, with the how father, I think I have to speed up a bit. Don't worry, you will still get it. So with a how father, right, we'll start with some simple logic and then we'll continue. So let's say I have 1, 0, 1, 1. I want to add it with 1, 0, 0, 1, like this. Now, for the first part that I'm going to add, right, I am going to add 1 to another 1, basically. So it means I have 2 inputs adder that I'm going to implement here. And then that 2 inputs adder is what we term as a half adder. Now here, in binary, what you do is, it's just like decimal. In decimal calculations, what you do is, if you have 39 plus 48, you do 9 plus 8, which is actually 17, right? And then you say, how many times can 17, or let me say, how many times can I get 10 from 17? You say 1. So 1, normal. So you write 1 here. And then what will be your carry? Remainder what? Remainder 7, right? So you carry this 7 to the next stage. And then you leave the 1 here. That's how we do decimal addition. Now it's same as doing binary addition. Also, in the case where let's say you have 79 plus 11, you have 9 plus 1, you get 10. With the 10, you ask yourself, how many times can I get 10 here? You say 1. And then, would there be any remainder? No. Think here I made a mistake. The 7 should be here, then you carry on 1. Yes. So the remainder should be here. You guys didn't tell me. The remainder should be here, then you carry on the 1, right? So the remainder is 0 because you will not get any remainder. And then 10 can go into 10 just once. So you write the remainder, which is 0 here. And then the 1 will be carried on like this. Do you get it? That's how we do decimal addition. So now we are going to implement this using the same logic. So the logic here will be that if I have 1 plus 1, I have 2. Now, the highest number you can get in binary addition is 2 because it's, let's say 2 is starting from 0 to 1 in a way. Let me say it's 0 to 1. And then in binary, 0 is 0, 1 is like this, and 2 is 1, 0 like this. So it's just like decimal addition. When you get 10, it's 1, 0 in a way. Here to 2 is 1, 0. Now, if you do the addition and then you don't get 2, you get something below 2, then you can write it there. So maybe a 0 or 1 and place it there. But when you hit 2, which is the maximum number, then you can ask yourself that how many times can I get 2 from 2? It's once. Remember what's a 0. So you write your remainder here, just like how we do in maths for decimal addition. And then it went into 2 once, then you carry your 1 here. So it's 0 carry 1 like that. Now, when you get to this stage, you have 3 bits coming to add. Now, when you have 3 bits, that's where we employ the big brother of half adder, which is what? The full adder. So that one helps us to implement 3 bits adder, basically. So that one, your carry out, which you had in your first stage, is serving as your carry in for the second stage to be added. So C in plus A plus what? B in that case will be your your full adder. So let's move this to the digital system approach that we use to design these blocks. So for a half adder, we are saying we are going to use 2 inputs, right? The 2 inputs, let's name them A and then what's a B. We can have a sum here, and then we have a carry out, which we saw in what I just represented. So when you have this, you have 0, 0, 0, 1, 1, 0, and then 1, 1, like this. Now with this, here, what you can see here is, if you want the sum is what you write after this addition. So 1 plus 1, we had 2. We said the remainder is 0, so the sum is 0. This is the sum. And then carry 1. So there's the carry out. So whenever you get 2, you have this. If in decimals you get 11, you add some 2 numbers and then you get 11. 10 can go into 11 once, right? That will be your carry. Remainder a 1. So that 1 will be your sum in a way. So if you have 9 plus 2, you say 9 plus 2 is 11 because 9 plus 2 10 can go into 11 once. That will be your carry. Remember what? 1. So this comes to add to nothing here, like a 0. Then you get 1 here, 11. So here too, if you have 3, it means 2 can go into 3 once. Remember a 1. So it means the sum will be a 1, and then you carry in a 1 in that case. So here, let's fill this table. So you have 0 plus 0. The sum is 0. The carry 2 is 0. So 0, you don't carry anything. When you have 0, 1, you are adding 0 to 1. The maximum is here is 1. So the sum is going to be 1. The carry out, you didn't carry anything. So 0 here. Then 1, 0 is just like 0, 1. The sum is 1. The carry is 0. Now here you have 1 plus 1, which is what? 2. I can't write 2 as the sum. Just like if you get 10, you don't write 10 as a sum. But I do 0 carry 1. Here too is the same thing. If you have 2, because it's binary, we are going to get what? The sum to be a 0, just like what we did here. And then carry what? A 1, like that. So it means if you are implementing a half adder, the sum will be a combination of the inputs as this. You check, since we are using main terms, we would check where we have 1 and then write the expression for it. So that's the sum. Now, the bits are changing, giving you a height. When the bits are the same, it gives you a 0. So we can say it's XOR, basically. Or if you draw a 4 input scheme up, you get 0, 1, 1, 0 like this for the sum. A and then B, 0, 1, 0, 1 like this. So you get A bar B for here. And then here you get A, B bar like that. So A, B bar. And this, you know, is what? A XOR what? B like that. So that's the sum for a half adder. Now for the carry, you could only see a high here. The rest are all zeros. So it means we just have to write the expression for this guy. Meaning the carry out for this half adder will just be A, B, because both of them are high. So A and then B. So with this, right, we can have a circuit for this, which would actually look like this. Let me zoom in so that I can be writing here too. So here, your 2 inputs half adder is A, B, and then the sum is an XOR. Sorry, XOR like this. This is your sum. And then your carry, you can tap here. It's like a short wire, so it's still the same signal. And in here, but then it's what's AB. So you need an AND gate. So I'll AND them together, and this will be my carry out. So let's say you are adding this to this. 0 plus 1. The sum says XOR them. So do 0 XOR 1. 0 XOR 1 gives us what? 1, right? So the sum is 1. Now, what will be the carry? The carry says multiply the 2, 0 times 1, which gives us a 0. So you can see here that we don't, since the carry is a 0, basically. But then if you move on to the next stage, which is 1 and then 1, sum says XOR the 2 together. 1 XOR 1 becomes what? A 0. And then the carry out will be 1 times 1, which is what? A 1. So the sum will rise there as a 0. And then we'll carry on a 1, which will come here, making 1, 0, 1. I think this makes sense. I need you to respond though. Is it making sense? Okay, sure. So, okay, someone is asking a question. Please, will this not give us A, X, nor B, X, nor C, A? Oh. Sorry. Sure. Sure. I think we're implementing XNOR, right? So it should be the same. Now you still want to get the output back. The output for the first one from this question, the output for the first one is A XNOR B, right? Yes. Then you go and XNOR with another one, go and XNOR with another one, go and XNOR with another one. Oh, okay, I get you. I get you. Yeah, it's like I'm coming. Let me come here. If you understand this, let me clean this first. So actually, yeah, I think, let me correct that. Since it's going to be this for the G, implement this one first. So it should be XORs, XORs, hardware this with this, another XOR. Then this goes through another XOR like this. Then the output is rather noted, basically. Yeah. So you XOR all of them, then you bar the overall output, basically. I think I've answered your question. So it's supposed to be like this, not XNOR, 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 XNOR. Have I answered your question? Have I answered your question? Oh, okay. So you are saying the hardware is confusing you. So actually, I'm correcting this. Implement what is under the bar first, which is normal XORs. Then at the end, put a NOT gate on top of all of them. Then you get your generator here, basically. Now, this thing that I did here, you see, someone was asking this. We want to get this as G, right? Let me clean this. So we want to get G at the output, but we are supposed to implement with 2 inputs. But we can't say this will give us G, because when I do 1 XOR 1, I'll get what? A 0. When I do 0 XOR 0, I'll get what? 0 in a way, right? Now, when I do 1 XOR 0 or 0 XOR 1, I get a 1, right? Sorry, 1 XOR 0 or 0 XOR 1, I get a 1. So for me to get G here back, I have to implement, we are using main terms, I have to implement a 1 and then a 0. What is a 1? 1 is G in a way. Then XOR with G bar, then you get this, right? So this is looking like J is high. Then 1 bar means a 1 in this case, in a way. So J is actually a 1 in this case, right? In main terms. So basically, we are still getting the G back in a way, basically. If you do 0 here, a 0 bar here, then you get G bar, which is, I get you. So you get a 1 here. But basically, yeah, in a way, he wants you to hardwire them, actually, basically. He wants you to hardwire them in some way, but he will just take it like that. Now to continue with the 4 other. The 4 other is when we're having 3 numbers coming to multiply. So we had maybe a carry of 1 here, then wanted to add with this and then this. So this is seen as our A, this is seen as our B, and then this is seen as our carry in. So here you have 3 inputs coming to the 4 other. And then still we are supposed to get a sum and then a carry out. Now, to do this, since we have 3 inputs, it means we are going to get 2 to the power 3 possibilities, which is 8. So we have A, B, C, in, right, as the inputs, and then we have the sum and then the carry out like this. So you have 0, 1, 0, 1, 0, 1, 0, 1 like this. Then here you have 0, 0, 1, 1, 0, 0, 1, 1. Okay. Then 0, 0, 0, 0, 1, 1, 1, 1 like this. Okay. So here too, when you add 0 to 0, then add it to 0, you get 0, carry 0. When you add 0 to 0, you still get 0. Then you add 1 to it, you get 1. So the sum is 1, the carry is 0. Here you add 0 to 1, you get 1. You add 1 to 0, you still end up getting 1. So it's still 1, carry 0. Now here you add 0 to 1, you get 1. Then you add 1 to the next one, you get 2. So 2 means the sum will be a 0, and then the carry will be 1. 0 carry 1 when you get 2. Here 2 is 1 plus 0, which is 1. And then 1 plus 0 is still 1. So you get the sum is 1, the carry is 0. Then when you do this part, you get 1 plus 0, which is 1. And then 1 plus 1, which is 2. So 2 becomes 0, carry 1, right? So sum carry out. Then here too, you get 2 because 1 plus 1 is 2 plus 0 is still 2. So the sum will be 0, the carry will be 1. And then here you have 1 plus 1, which is 2. 2 plus 1, which is 3. 3 means you have the sum to be 1, and then you carry out 1. So this is how your table will be looking like. So with this table, we are still supposed to draw for the sum and then the cout in this case. So here, what we'll do is we can use K-map. Actually, we can use K-map, or we can write the terms one by one if you want. But for something to come out clear, for the carry out, we'll write it from here one by one. And then the sum, I'll use K-map. I want something to come out clear. If you use K-map, you will still end up getting the same thing, but it wouldn't come out clear. So here, the sum, this is for the sum. So the sum, we have the first 4 bits as 0, 1, 1, 0. So we'll fill 0, 1, 1, 0 here. Then the last 4 is giving us 1, 0, 0, 1. So you have 1, 0, 0, and then 1. And then I've told you this looks like an XOR gate. So it means the sum is just A XOR B XOR C in like this. Now, let's write the Half-Adder equations here. Sum was A XOR B. Carry was what? AB. Now, this is looking like a half-adder. Just note this for now. Now, let's do the carry out. Now, for the carry out, we are going to write the expressions one by one. So here, what gave us this first one? It was A being 0, B being 1, C in being 1. So we have A bar, B, C in. A bar, B, C in, like that. So that was this part, giving us a 1 here, right? And then we have another one.
When are you done?
You said
A.
Oh. Okay. So here too we have 101. So 101 means we have OR. 101 means A is high, B is 0, so it should be bad in main terms, and then C in should be a high. So we have this first two. Then the next two we'll have this also giving us Li, which is here. So that one we have A, B, and then C in bar, because C in is 0. So A, B, C in bar, like that. And then the last one giving us 1 here. 2 is 1, 1, 1, which is A, B, C in. So we have A, B, and then C in here, right? Now with this, let's minimize this. Now in minimization, we will look for like terms. So here you can see C in, you can see C in. What is left is A bar B for this part, and then AB bar for this part. And then this whole part, the like terms are AB and then AB. So we can place AB out and then factor in C in bar or C, right? C in a way, C in. Now, when you have C in bar plus C in, it means you have like 1 bar plus what's 1. So it means 1 bar plus 1 gives us a 1. So this goes to 1, and then we'll be left with just AB, right? So this part becomes AB. And then this part, when you have A bar B or AB bar, we are saying that expression is AX or what? B. And then you have C in multiplying it. So the carry out is seen as C in into AX or B or plus AB. Now, when you look at this carefully too, this can be received from a half adder. Basically, this can be the sum of a half adder, And then this will be the C out also of a half adder. So it means in a way we can implement a full adder using a half adder. But then let's look at this. Let's look at this. Please, do you have any question for me up to this point? If you have a question, you can tell me. Do you have questions on this? Because I'm coming to show you something. And can I clean it? Let me do this. Okay. So I'm cleaning the table. So actually we can implement full adder with a half adder, and in a way a half adder to with full adder, like in reverse states. But then let's see, if we have 2 inputs, right? We are saying we can get A XOR B as the sum. So this will give us the sum, A here, B here. And then we'll have the carry being this, and AND gates, the carry out. Now the carry out is actually going to be a carry in for the next stage, basically. That's what mostly happens. But then if you want to implement a full adder, we are saying that we can implement a full adder with 2 half adders, because when you check the expression for the full adder, the sum is A XOR B XOR C in. So what I'll do is the A XOR B, let me represent this with X. So I'm replacing A XOR B with X. So it means I have the sum to be what? X XOR C in. And then for the carry out, I'll place X here too, right? So it means the carry out for the 4 adder becomes what? C in X plus AB. Now let's forget about this AB for now and then concentrate on these two. What can you see there? You can see that when I have a half adder of 2 inputs, when I want the sum, I will just what? XOR them together, and there's it. So here I'm seeing it as X and then C in of a half adder, like being inputs of a half adder. So meaning you have something like this, X and then C in half adder. I'll get a sum, which is this that you are seeing here. And then the carry out should be the 2 inputs multiplying like AB. So here I'm having C in times what? X. So it means I can generate 4 adder with 2 half adders. And then this AND gate here will come and then add to the carry out of the next half adder, which is this guy. I'll just come and add the output of this guy to it to get the 4 adder. So let me draw what I'm trying to explain here. So it means that I can have the first 2 inputs, A, B. If I want to design a 4 adder, I can have A, B, and I'll XOR them to get a sum. I'll come and tap here, and them together to get the carry out. Now after this signal is A XOR B. This signal is AB. I can see those expressions here and then here and then here, right? So what is left is this guy. Now I can place another half adder and see this A XOR B as X. So let me say this equal to X. Now this X will be XORed with another input, which is C in coming from here. So the C in will be XORed with this. And then what will be the output? X XOR C in. And then you ask yourself, what is X? X is what? A XOR B. So it means in that case, the output of this signal will be X XOR C in, which is the same as A XOR B, which is the X XOR what? C in. And then when I tap from here, which is the X, and then the C in, I'll get the carry out of this half adder, which is what? X C in. And then you ask yourself, what is C in? C in is what? Sorry, X. X is what? A XOR what? B. All by what? C in. That's it. So this is the first part of this part. Then now I'll just go and add it with this AB to get the whole carry out, as in the actual carry out. So let me name this first C out C1, right? Then the actual carry out, let me clean this part for me to draw it. Clean this. So it means I'll just come and tap this output, come here, and then all them together, because this signal is AB, and then this signal is A XOR B multiplying C in. And then when I all them together, not XOR, when I all them together like this, it means that will be my actual carry out of the 4 adder, which we had here, C in into A XOR B plus what's AB, like that. So it means I've implemented a 4 adder using 2 half adders and an OR gate. So a 4 adder is 2 half adders plus an OR gate. An OR gate, which is this guy. That's a 4 adder. So in a way, I can basically draw black boxes around these things. So this is the first half adder. This was the first half adder. And then another black box here, the second half adder. and there's the OR gate coming. So what I'll do here is I have first half adder like this, which was A and then B. Now the sum and then the carry are here, and then C in is coming, right? What did I do? I passed C in and S into another half adder. And then what I had was, here was A XOR B. When I pass it through a half adder, what will be the sum? The sum will be A XOR B XOR C in. So A XOR B XOR what? C in. Then the carry out here will be this signal times this signal, which is C in multiplying what? A XOR what? B. Now, in the expression for the full adder, it should be this plus AB, which is here, as the carry out. So I'll pass it here and then put an OR gate here. So that would be the actual carry out of the full adder. So this is the implementation of a full adder using two half adders and an OR gate. I hope this makes sense. Does it make sense? Okay. So actually, this half adder and then full adder implementation too, you can do the same thing for the subtractors. I don't know if we should do that, or if you would want us to check your mid-term question, that would be great too. I think when we're starting this, someone was suggesting that we do the parity, the half adder, and then what was the next one? If you can remind me. Okay, let's just check your mid-term paper. I think they've sent it to me here. I'm coming. Hey, relax. I'm coming. Okay, I think it's here. Sure. So okay, so this was your medicine, right? Now, with this question, for instance, I think what you guys were supposed to do was actually odd parity checker. So you had to do this. So yeah, I think that was that. Then this question in particular, yeah, this one. Okay, so this is it was saying the following circuit is constructed from two full adder modules and AND gates. The inputs are A, B, C, X, Y, and the outputs are P and then R. So here he wanted you to know the expressions for the full adder straight away. So the full adder, we realized that the sum is the XORing of the three things, three inputs. And then the carry out was when you multiply this, then you add AB to it. That will be your carry out. So in the same way, this question, these two inputs, and then you have a C here. The C here, if you have your sum will be A XOR B XOR the C. And then your carry out, which is here, will be AX or B times what? C, or plus what? AB. So actually, what he did was, you see here, he introduced something to this. Let's see. This is the XORing of the three signals, right? And then this was the actual carry out, which you should get. Then that one is fed as an input, which is C in to the next stage. So it means when you go to the next stage will have a whole 4 other expression as the carry inputs, basically. So it means you would have something like this. You have a 4 adder with inputs AB, and then a carry in coming out from that part. But then I think he added them together. So the whole expression, the sum times the carry out of the first 4 adder stage was given as what? C in. And then here, let's say your sum is A XOR B XOR C. And then your carry was A XOR B or by, so let me make here square brackets, or by C plus what's AB like this. This your whole C in. So your whole C in is this. So the sum that will be here, and then your carry out that will be here, will just be something like this. So your sum will be this AB and then this whole C in. So AB and then this whole expression. That's all. And then your carry out will be this times this. Sorry, A XOR B, or by the C in, which is the whole bracket, plus AB. Then you are done with the question. So that was what the question demanded from you. So here you can place them here, XOR C, and then here is A XOR B, or by C plus AB. You can do same here, That'll be your sum and then your carry out. Then you get your 4-5 marks. That's all. So he wanted you to just know the expressions for finding the 4 adder. Now, let me go through this multiplication thing too with you. So the whole thing is, we say that multiplication is just repeated addition, right? Is anyone saying anything? I think I have to bring this back. So what I was saying is this: multiplication is just repeated addition. So with a multiplier, if you are asked to design a multiplier with the first number having 3 bits, and then the second number having 2 bits, like X is X1, X0, X2, like this. And this times, let's say Y, which is Y1 and then Y0, like this. It means you do it just like having X times Y. Now here, since this is 3 bits, you have to represent it this way. And then your Y1 and then your Y0 will come and multiply. Now, when you do your first multiplication, this guy should multiply all these 3. And then your second multiplication will be this guy multiplying all the 3. So the first one, you get Y0 times X0. So X0, Y0, you leave it there. Then the second point will be Y0, X1. So X1, Y0. Third one will be Y0, X2, which is X2, Y0, like this. Then this guy goes to multiply. So this one too, Y1 multiplying all of them. So you have X0, Y1, X1, Y1 here. Then you say you add all of them. you add, right? Because when I give you 38 times 49, you do this times this, you write it here. This times this, write it here. This times this, write it here. This times this, then you write it here. After you do it, you add them, then you get your answers. So here too, if you are going to add and then there is binary, you should bear in mind that for a binary addition, you are going to implement it with an adder, and then the adder should have a sum and then a carry out, because let's say you multiply and then here was 3, here was 9, here was 8, here was 6, right? 6. Then you are coming to add. Here will be 9 plus nothing, so you get 9. Here is 3 plus 8. 3 plus 8 is 11. So you get 1 carry 1 like that. So here it means it's a 2 input adder, which is giving you a sum, which is this one, and then a carry out, which is this one. It could be that the next stage will be 3 inputs. 3 inputs means you should implement it with what? A 4 adder. So in that case, what it means is here you have an adder here. Here too, you have another here. And then something will come here. So since this guy is not adding up to anything, it's just X naught, Y naught, which in your exam, he denoted that one as P, maybe P naught. You can use any letter that you want. Then here, you know that this signal should give you a sum and then a carry. So the sum will be here. The sum, he represented that one with P1, which is the sum. And then the carry out will Can you see my screen? Okay, let's continue. So here, in this case, your carry out that you end up getting here will be fed as a carry input here. So it means here you are going to get 3 things adding up. So here you are supposed to implement it with a 4 adder. So here you get another sum, which is say P2, and then a carry out. The carry out will be taken here, which is, let's say, carry out 2. So it means here you are going to implement it with a half adder in a way. Then here too, you get a sum, which is P3, and then a carry. The carry will be, say, P4. So you end up getting this whole answer, right? So now, in drawing the circuit for it, you are not supposed to use the XOR plenty things. No, you just have to represent them with black boxes. He knows that you know that you are supposed to get a sum and then a carry. So you don't need to really worry about you writing the expressions for it. So here, you can draw your signals like this. So here is X2, here is X1, here is X0, here is Y1, Y0 like this. Now you ask yourself, what's the first thing here? X0, Y0. So I come and tap. X0, Y0 means I should add them, and that's my P0 like this. Then here is X1, Y0, adding up to X0, Y1. So I first have to implement this and this. Then I'll take it to a half adder. Or if he says implement with just 4 adders, it means that first stage, your 4 adder will have a carry in of 0, basically. So here you do X1, Y0 first. So X1 is here, Y0 is here. You add them, then you relax. You place X1, Y0 here so that you not be confused. Then you come and do X0, Y1. So X0 is here, Y1 is here. Then you add them together. Then these 2 inputs are supposed to be fed to a half adder because you have to add them. If he tells you to do 4 adder, it means your carry input here, C in, is actually 0, like this. Then here you are supposed to get a sum, which is P what 1, and then a carry out 1. Now this carry out 1 should be taken to this part, right? This part to be added with these two guys. So in that case, you are going to get an actual 4 adder with 3 inputs, x to y naught. So x to y naught, we have to add them, and these two guys, x to y naught, like this. Then the next one is x1 here, x1, y1. So x1 here, y1 here too. You add them. Then the last input to it is this carry out. So the carry out will serve as an input like this. Then since you have 3, it means you are supposed to use what? A 4 adder. And then that 4 adder will also have a sum, which is what we are showing as P2, and then a carry out 2. So carry out 2 will also be taken on to the next stage, which is this part, which we are going to get carry out 2 plus what? X2, Y1. So we will implement x2 and then y1 as this, x2, y1. And then this will be taken on to the next stage. If it tells you to implement with just 4 others, you should know that your C in is 0. So you can place a ground here, 0. So here too, I can place a ground here like this. It means it's a 0. Then my output will be what? P3 and the C out 3, which is actually giving us what? P4. So this is the same as P4. Then you are done with the implementation of the whole thing. So this is what you do in binary multiplication, basically. So I think that's for your midterm. Those were the most challenging things that you were encountering. If you have any question, you let me know. It's almost time. Yeah, talk. Unmute and then talk. Emmanuel Opon.
Please, what if the in the first multiplication the x naught y naught? Yes, practically, what if that one gives you a 2-bit number? You see here, we wrote it as just P naught. Please, do you get
me?
I
am coming to answer your question, basically. Okay, so the whole point is this, right? If you are doing this x naught, y naught, let's say x naught is 1, y naught is 1. When you multiply them, x naught, y naught means multiply. You get what? 1 bit. If it's 0 times 0, you get 0. 0 times 1, you get 1. Sorry, 0. 1 times 0, you get 0. So in any case, you are supposed to get 1 bit there, right? Do you get it? Do you get it?
Okay.
Yeah, actually. So this goes to an AND gate, but the bit that you end up getting here as peanuts will still be a 1 bit. Do you get it?
Yeah, sure. I get it now.
Yeah.
Thank you.
You're welcome. Please, any other question? Any other question? Or you are cool with this? I think maybe let me ask this person. She seconded Fahim Idrisu Sumaila. Okay. Do you get everything here? Please, do you have any concern, any issue? You let me know. With this thing, I would come and then address it. This hardware thing, yeah, I have to come and address it. Try. Okay. If there are no questions, then I think our time is almost up because it was scheduled for 2 hours or so. Or the time is not yet up. I don't really know. Is the time up or we still have time? Okay. The ending time is 7:30, so we still have time. So please, I would like to know the next thing we are supposed to do. No, it's not 5 minutes more. I think it's to 7:30. Yeah. So the class will end at 7:30. I thought it was 6. So any additional thing that we are supposed to do, or we should go through subtractors too? I would like to hear from you. Should we do subtractors? You can all unmute and say yeah, then we can continue with it. Or else, if one person just says we should do it, then there will be some way. Maybe you don't want to do subtractors. Okay, I'm seeing just 3 people here. Okay, you normal. Let's do subtractors then. Okay, so with subtractors, it's just like how we did the others. So I'm cleaning everything here. Everything. Let me see. Okay. Okay, so let's do subtractors. Now here too, just like you do decimal additions, right? Or let me say decimal subtraction. Here, if you have 1 0 1 0, then you have 0 0 1 1 like this. And you are supposed to subtract. In decimals, if you have 38 minus 49. Here, the first stage, I just want you to see this so that we can factor in the borrowing aspect of the subtractor. So if you have this, say 8 minus 9 can be possible. Although it's possible, it can be possible. So you go and borrow. When you go and borrow, it becomes a 10 in decimal. So here it reduces to 2. You go and take 1 from here, all right? But then here it's seen as 30, right? So you go and borrow 10 from this to make it 20. So it will be seen as 2. Try. So you come and add the 10 you've borrowed from the 30, because decimal place here, if you are doing place values, is 30 and then 8, right? So 30 tens and then 8 ones or units. So you borrow 10, then you come and add to the 8 here, making what? 18. Then you come and do your subtraction, right? It's the same for binary subtraction, where in this case, if you are going to borrow, you reduce the number to, let me say you just reduce the number by 1, right? Then the borrowed number you are going to add up to this 8, in this case, will be 2, will be seen as 2. So here, if we want to do 0 minus 1, say it can be possible. So we come to this guy and come and reduce his value to 0. But when we borrow, we are borrowing 2 to add up to 0. So 2 will be seen here. Then we do 2 minus 1, which is what? 1. Then we can have it there like that. Now here 2 is 0 minus 1. It can't be possible. We come here, we can't do it. Wouldn't work. So we come here to borrow, reduce it to 1, and then place 1 here, right? Sorry, 2 here. Sorry. We borrow, it becomes 2. Now when it becomes 2, we need it here. So here too, we borrow 1 from this, like 1, 2 in a way. So here reduces to 1. And then what we will borrow to here will become what? A 2. Then we say 2 minus 1 becomes what? A 1. And then here 1 minus the 0 becomes what? A 1, like this. So here, if you check the answer is giving us 111, which is 7 in decimal. Now 1 0 0 0, right? If I did this well, 1 0 0 0 is what? Hey, relax. So this becomes a 2 1 minus 0. Yeah, actually, yeah. So this will be the answer basically. Yeah. So this is what we are going to get. So here too, just like what we're doing in the others, we'll have a difference here because you are finding the difference between two numbers in this case. So you have difference, you have D, and then you have borrow. If you are supposed to borrow, you have a borrow there. So here, let's say you are designing for a half subtractor. A half subtractor will have two inputs like this. Let's say A and then B. And then the output will be the difference and then borrow out. Sorry, borrow in. Yeah, in a way. Just borrow or borrow in, whatever. So you have 0 0 0 1 1 0 and then 1 1 like this. So if you have this, what it means is when I have 0 minus 0, I get a 0 here, and then I didn't borrow anything, right? So here is 0. Then I have 0 minus 1. There's a big problem here. So I have to go and borrow, right? What I will borrow is actually 1 of 2 in a way. It's 2, but it's just 1 that I borrowed. So it means I borrowed 1 in a way. Because when you do 88, 49 like this and this one goes, you leave 1 here, right? You come and add 1 to like this to this in a way. So you went to borrow 110 in a way. 10 times 1. You borrowed 1 of this 10 to be used here. So you borrow 1, which is 2. Actually, in actual fact, is 2. Then you come and do 2 minus 1. So because you borrowed 1, which is 2, you come and do 2 now minus 1, which will give you what? 1, a difference of 1 here. That's what it means. Then here too, you have 1 minus 0. So that one there, it gives you 1 straight away. And then you get a 0 here because you didn't borrow from anyone. And then here 1 minus 1 is just 0. You didn't borrow, so it's 0. Now seeing this is what is giving us a high. So if you check the half subtractor, the difference is just A, X, or B, right? The difference. If you check this well, because that's only what is giving us 1 or a high. Then the borrow is just this place. So that one, when you check the inputs, is A bar and then B. So B is A bar and then B like this. So this will be the difference. This will be the borrow in this case. If you have a half subtractor. So in a way, it's looking like the half adder, but then here you have a bar. Now we can go on to check for 3 inputs, which is the full subtractor. If you have any challenge here, you tell me. Like, if you have any question, is it clear up to this point? Binary to gray code, RCD and things. Oh, okay. If we can solve questions, okay. So other people too were suggesting some other things. Let me finish the subtractor and then we'll do that. Okay. So with this, if you want to implement a full subtractor too, you have to go with 3 bits, right? Because you have a borrow in addition to the 2 things you are going to subtract. So it means in that case, you would have A, B. If I should use borrow in, and then you get a difference, and then let's say B naught. So 0, 1, 0, 1, 0, 1, 0, 1, like this. So here you have 0, 0, 1, 1, 0, 0, 1, 1, then 1, 2, 3, 4, 1, 2, 3, 4, like that. Now, so here you do 0 minus 0, which is 0. Then that 0 minus this next 0, which is also a 0. That's what you'll be doing. So this is 3 input subtractor. So you first subtract the first 2. The answer that you get, then you subtract the last one from it. So here you get difference of 0, B naught of 0. Now when you go to the next stage is 0 minus 0, which is still 0. Now that 0 minus this one, it can't be. So we would have to go and borrow 1, 2 in a way. So we will go and borrow here. So the borrow B naught will be 1. And then that 2 now will come and subtract this 1 to give us what? A 1 here. That's how we do it. Then when you go to this second stage, you have 0 minus 1. 0 minus 1, it can't be. So we have to go and borrow something from here. So you borrow 1, 2. Then you get 2 here minus 1. 2 minus 1 is what? 1. Now that 1 that we are getting now minus this 0, then you get what? 1. So you end up getting 1 here. Then the next stage, you do 0 minus 1, which can't be. So you go and borrow 1 like this. Yes, you go and borrow. Then you get 2 minus this 1, which is 1. And then 1 minus 1 gives us what? A 0. So the difference is a 0, like this. Then the next stage, here you get 1 minus 0, which is a 0. Sorry, which is a 1. And then that 1 minus this 1, you get 1. So here you didn't borrow. So here 1, which is the difference, and then the borrow is 0. The next stage, you do 1 minus 0, which is 1. And then that 1 minus this 1 gives us a 0. So the difference is 0. You didn't borrow. Now, this last but one stage is 1 minus 1, which is 0. And then that 0 minus this 0 gives us what? A 0. You didn't borrow. So this. Then here, you have 1 minus 1, which is, how do you call it? 0. And that 0 minus 1 gives us something we don't want. So you go and borrow 1 here. It becomes a 2. Then the 2 minus 1 gives us a difference of 1. So this is the table you end up with. Then you go and draw your K-map for it. That's all. So if you check the first 4 parts is this. And then the last 4 parts is also this. So if you check the first 4 parts, you have something like this. I'm coming in. Something like so the first 4 parts, let's say you draw K-map for this subtractor. You have A, and then B in. You have 0, 0, 0, 1, 1, 1, and then 1, 0, 0, 1 here. So the first one is 0, 1, 1, 0. So 0, 1, 1, and then 0. The last one is 1, 0, 0, 1. So here it's looking like an XOR again. So the subtractor has its difference for 3 inputs still remaining as XOR. So A XOR B XOR C in like this. Then if we are to check for the B notes, the B notes will have something like this. This A, B in 0, 0, 0, 1, 1, 1, and then 1, 0, 0, 1. Or we should have, now let's write the expressions one by one. Mostly if you do the K-map, you will not see something clearly in a way. So let's use the K-map, the outputs one by one. So this, and then this last guy. So B notes will be giving us, the first one is 0, 0, 1, giving us a 1 here. So 0, 0, 1 is A bar, B in 0, 0, 1. Or the next one is 0, 1, 0 here, giving us a 1 here. So 0, 1, 0 is A bar, B in also bar, right? Then, or the next giving us one is 0, 1, 1. 0, 1, 1 is A bar, B, and then what? B in. Or the last one is all of them being high. So that one is A, B, and then what? B in like this. Now, if I want to minimize this, when you check the first expression with the third expression, this one and this one, you realize that we can get A bar and then B in coming out. And then inside of it, we have this. Inside of it, we'll have B bar or B. This goes to 1. So you have just this. Or this and this guy too. We can have A bar and then B. And then inside of it, you have, did I do any mistake along? If I did, let me know. Here you have B in bar or B in. So you'll be left with A bar B. I think I've made a mistake somewhere here. Let me check it. So here I have this. The third expression, it was A bar B and then B in. Okay. So let me put the bar there. A bar here. And then I have this, I have this. Is there any mistake here? Tell me if I've done any mistake here. Yeah. Let me see. Okay. So let's see. So here, you end up getting, see, A bar, B bar, B in. Here is A bar, B, B in bar. That's the second one. And the next one is A bar, B, B in, actually. Yeah. So if I do the last one, I will get this, right? 0011, 0011. Okay, sure. So I'll get here A bar coming out, B in coming out, and then B bar or B. So this goes. So I'll end up getting this and then this guy as my B note. Then you go and draw. So here to your subtractor, you end up with something like this XOR for the house subtractor, A and then B. This will be your difference still, because we inputs, then B in comes inside. Then to get your B notes, you just look at the expressions here, then you implement them with your signal. So maybe A, B in will be this AND gates. And then another one is A bar. So you pass these through a NOT gates. Then you multiply with B like this. B you and then the whole thing goes to an OR gate. Sorry, an OR gate like this. Then you get your B out like that. So that's how you implement subtractors too. Yeah, basically. Any question? So those of you who are saying that we should do this one, the last thing we're taught in class, binary to gray code, RCD and things. So I'm coming to display your slides, then you tell me where that one is actually. So this is the subtractor, right? So XOR with the first two inputs, you get your difference, and then your B note will be something like this, A bar B. If you have three inputs, things change actually. Yeah, you have something different coming out of your circuit. This can we look ahead? Okay. So it means you guys have started encoders and all that. Relax. Please tell me where your binary to gray code and all that is. But let me teach you this. Binary to gray code. Gray code, the whole idea of using gray code is to have bits changing as you are moving from one point to another by 1. So if, let's say, you have, I'm coming. Let me use this to show you something. So let's say you have 0, 1, 2, 3, 4, 5, 6, 7, 8, like this. And then you want to change this to gray code. This decimal. So maybe BCD is binary to decimal converter, basically. So this is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and then 1, 0, 0, 0. So let me put all zeros here to make it 4 inputs. Now this is 0 to 8, basically. If I want to implement this BCD, so this is just decimal to binary or binary to decimal, whatever. There is this. Now, if I wanted to, I want to use gray code for it. For gray code, we are saying that as I'm moving from 0 here to 1, as you are moving from 0 to 1, the binary bits should change by 1. So here, I can implement this as 0, 0, 0, 0, like that. Normal. Now, the next stage from here to here, these bits should just change by 1. So I can use 1, 0, 0, 0. It means this place has changed. It has flipped by just 1. You shouldn't have 2 bits flipping at the same time. Someone too can say, oh, then I can use 0, 0, 0, 1 from here to here. That one to this last bit flipped. So with Gray code, you can have a lot of people doing what they want. There is no restriction unless he tells you that there is the order you are supposed to use for it. Else, there is no restriction on Gray code. So here, if let's say I'm going with what I did initially, or let's use the normal logic that you know. So in Gray code, I can move from 0 to 1 actually, because here the bit has flipped here, just this part. Then when I'm going to 2, I have to flip this bit also by just 1. So if I write 1, 0 here, here has changed. So it can't be possible because we are using Gray code. So I have to use 3. 3 is 1, 1, which is 0, 0, 1, 1. So here is remaining the same, but here has what? Flipped. That's the whole logic of Gray code. That's what you use in your K-map here. So K-map, you say 0, 0, 0, 1, 1, 0, sorry, 1, 1, and then what? 1, 0, because from here to here flipped. From this stage to this stage, here flipped. From this stage to this stage too, here also flipped. So it means you'll be flipping the bits, or it will be changing in one bit once at any point in time when you move from top to down or top to bottom. So here, maybe the next number that I'll use, I can go with 2 because 2 is 0, 0, 1, 0. So it means here, you see, here, this flipped. At this point, this flipped. And at this point, this one is flipping. The first 3 are remaining what? The same. So that's the essence of Gray code. So you can continue with this. Let's say someone will come up with it, with another thing. Note that there is 0, there is 1, there is 3, there is 2. So I can't use what I've used here already. I have to change to another value. So which other value could you think of? I use 1, 0, 0, 0. This is 4. And then with this, here has flipped, here has flipped. So it wouldn't work. So you shouldn't think about 4. If you think about 5 too, it wouldn't work. But let's try 6. 6 is 1, 1, 0. So 1, 1, 0. And then I put a 0 here. It means which parts flipped? Just here. When you check this and this, right? So 2 can move on to 6 in a way, in Gray code. So you can move from 1 to 3. If you move from 3 to 2, you can move from 2 to 6. Because you have just this part changing. Now the next number you can think of is what? Let's say you go for 5. 5 is 1, 0, 1. It means these 2 places are flipped. So you can't go to 5. Let's try 7. 7 is 1, 1, 1. And I put a 0 here. So if you check this one, it means these 2 guys are remaining the same, but this has flipped from 0 to 1. So I can go to 7. When I move from 6, I can go to 7 in Gray code. Then the next bit that I can have is changing this by 1 bit. If I want to change this by 1 bit, it would be maybe very difficult, but let's see. If we do 1, 0, 1, and I put a 0 here, it means the middle position here has flipped, right? So it means this is a 5, 1, 0, 1. So I can move from 7 to 5 in Gray code. Then from these two, you think of the next number. Here is 0 to 8. Which numbers have we used? 0, 1, 3, 2, 6, 7, 5. What we haven't used is 8. And then which one again? 4, right? So let's try 4. 4 is what? 1, 0, 0. So if you do 1, 0, 0, I put a 0 here. 1, 0, 0 means this first 3 didn't flip, but here has flipped. So it means in Greek code, I can move from 5 to 4. Then the last number I can have is 8 because I can make here 1, 0, 0, 0. But I check this, these two have flipped. So I can't have it that way. It wouldn't work. So which number will you go for from here? You can say 1, 1, and then 0, 0. 1, 1, 0, 0. The 3 here have no change, but here has flipped. But 1, 1, 0, 0 in binary is what? If you have 8 plus 4 is what? 12. So it's 12 like this. So if you want to change from BCD to Greek code, you can have it like this. So 0 will be seen as 0, 0, 0, 0. 1 will be seen as 1. 2 will be seen as 3. 3 is going to be 2. 4 is 6. 5 is 7. 6 is going to be 5. 7 is going to be seen as 4. And then 8 is going to be 12. Then they will just tell you to draw the output of this Greek code. So this Greek code outputs bits. You'll be using K-maths for each of them. And then here you are going to have 4 distinct outputs, which are, let's say I'm using Z. I'll get Z3, Z2, Z1, and then Z0. And I'll name here A, B, C, like this. So A, B, C, they're giving me this. Now here, when I consider Z0, Z0 is 0, 1. I'm using the numbers down here. Is 0, 1, 1, 0, 1, 1, 0, 0. So 0, 1, 1, 0, 1, 1, 0, 0, right? Then Z1 is the second down. So the second down is 0, 0, 1, 1, 1, 1, 0, 0, 0. So 0, 0, 3 ones, 4 ones actually. Oh, 1, 1, 1, 1, then 3 zeros. 0, 0, 1, 1, 1, 1, 0, 0, 0. Okay. 0, 0, 1, 1, 1, another 1. Then 3 zeros. Interesting. So this one, let me check it well. 0, 1, 1, 0, 0. Okay, so here is a 0. Before a 1, 1, and then a 0, 0. So 1, 1, 0, 0 like this. Then Z2 is this down. So this down is first 4 zeros. Then 1, 2, 3, 4, 5. How? 1, 2, 3, 4. Then 1, 2, 3, 4, 5. How? Am I seeing this well? 0, 0, 0. This is 0, this 1, this 3. All zeros, 2 is 0. Okay, so another 0. Then I have 1 here, 1 here, 1 for 5, 1 for this, 1 for this. Oh, okay. I actually have 9 numbers. I was thinking of 8, basically. That's why. So 1, 1, 1, 5 ones, 1, and then another 1. Then let's say this one too, I have 0, 0, 0, all the way down. Then the last number is a 1, like this. Let me check the first one. It's 0, 1, 1, 0, 1, 1. Okay. Then 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0. Okay, sure. So this is the output that you get. And then you have to draw K-map for this. So the K-map for this, if you want to draw the K-map, it's just the normal thing you've been doing. So basically, let me ask you first, can I clean it? And please, can I clean what I've done? Okay. Okay, sure. So I'm cleaning the BCD thing so that we'll draw the K-map for each of the outputs. So we'll do this. I'll clean here. Clean this part because it's the same thing that I've done there. So here, this for 0, this for 1, this for 2, this for 3, 4, 5, 6, 7, and then what's 8? The last one is 8. Good. So here, if let's say you want Z0, Z0 will be actually 16. What was happening? 16 K-map, or let me say 4 bits K-map. But the rest, we don't know. So we can use donkeys to replace them. And then I said, let's denote the inputs as A, B, C, and then D like this. So A, B down here, C, D up here. So 0, 0, 0, 1, 1, 1, and then 1, 0. Have 0, 0 here, 0, 1 here, 1, 1 here, and then 1, 0 here. So it means in this case, this 0, 0, 0, 0, that's a first, let's just fill the first 4. First 4 is 0, 1, 1, 0, right? Up to here. So 0, 1, 1, and then 0. Then the next 4 is up to here, which is 0, 1, 1, 0. Another 0, 1, 1. Sorry. Oh. Let me do this. Okay. 1 and then 0. Then the last bit we are getting there is a 0. So I'll place a 0 here. Right. A 0 here. Now, all these are not defined. So let's use XORs for them. Let's say we want to get the most minimized version of it. We are supposed to use XOR. And then when you have XORs in your circuits, it's not by force to use them. But if they can give you the most minimal expression or minimum expression, then you use them. So in this case, it's clear that if I go with this, I can combine. When you are doing the combination, you can do combinations of 2 to the power n. So you can do 2 to the power 0, which is 1, 2 to the power 1, which is 2, 2 to the power 2, which is 4, 2 to the power 3, which is 8. So you can't do 3 combinations. No, it wouldn't work. So here, I can group 4 of them using these 2 XOR gates. Sorry, donkeys. Sorry, not XOR, donkeys. So here, when I minimize, A and B are changing from here all the way down. So they wouldn't be even taken into consideration because A is changing from 0 to 1. When you move from top to bottom, B is also changing from 0 to 1, 1 to 0. So we wouldn't take them into consideration. We'll just focus on these 2 guys, which are not changing, which is supposed to be C bar because it's 0 and then D because it's high. And then another one we can get here is this guy. So this guy here too, A and B are changing throughout, but here C and D are maintaining as what? C being high and then D being what? Low. So C, D bar. So Z0 will be seen as what? C, X, or D when you have this expression. So this is your Z0. So when you XOR these together, you get this first part for each of them when you do this C, X, or D. So let's take an example. An example is having 5, right? 5 is here. 5, we're seeing 5 as 0, 1, 1, 1. 0, 1, 1, 1 is actually 7. The last bit is a 1. Let's see if we'll get a 1 now. C is 0 here. D is 1 here. If you XOR 0 and 1, you end up getting what? A 1, which is here. Let's take 1, that will give us a 0. So if we want a 0, let's use this 4 here. 4 was here. So 4 was seen as 6, right? So 4 is the C and D are 0 here and then 0 here. When you XOR 0 with 0, you get 0, which is seen here. So that's your Z0, basically. Is that clear? Please, do you understand? Then now, let's do for Z1. So Z1 too, we'll use the same implementation, basically. So the same implementation we've done for Z0. So I'll clean this one, but you keep Z0 as C, X, or D in your mind. Or if you are writing it, let's say Z0 is here, C, X, or D here. Then I will go to Z1. Z1 too, we'll use this 4-input schema for it. So A, B, and then C, D. 0, 0, 0, 1, 1, 1, 1, 0. 0, 0, 0, 1, 1, 1, and then 1, 0. So here too, the first 4 outputs end here. 0, 0, 1, 1 for Z1. Here is Z1, actually. So 0, 0, 1, 1, like this, right? Then the next 4 ends here, which is 1, 1, 0, 0. So 1, 1, 0, 0, like this. The last output is a 0. So 8 here is a 0. The rest I can use don't case so that I can take some to minimize to get the most simplest expression I can get here. So here, I can only group these 4 guys. These 4, and only group these 4. So those 4 guys, A is changing from 0 to 1 here, but B is maintaining as a high. So it means Z1 for that small portion is B. Now let's relax. Let's go to the top here. The top here too, because it's taking this whole 2 or the 4 things. So the top here too, C is remaining as 0, but D is changing. So we'll take out D, and then C is a 0, so it becomes C bar. Then or, because we are seeing something here, we have 1, 1 here, and then we have don't care. And then they've told you that you can do looping. So you can do top to bottom, side to side, you can do here to here, and then down and then bottom. So here I can group these 2 guys, and then group these 2 guys too, giving me the 4. Now when I check here and then the last one, so here and then here, A is changing from 0 to 1, but B is remaining at 0. So B will become bad in main term. And then here too, I have C remaining as a high throughout, but then D changing from 1 to 0. So C will become what? Normal C like this. Then I'll get Z1 to be what? B, X, or C like this. So Z1 is also just XOR. Z1 is just XOR. So Z1 is B XOR C like this. Then it means, let's say we are taking another example here. Let's take 3. 3, this is Z1 for it. It's supposed to be 1. So 3 was this. When I XOR B with C, it's 0 XOR 1. 0 XOR 1 is a 1, which is here, right? When I take, let's say 4, 4 2, I should get a 1 here. 4 was here. B and C is 1 XOR 0, which is a 1. Let's take 1, that will give us 0. So 0, let's choose, let's say 8. 8 is 0 here. Z1 is 0. Now when I go to 8, it's B here, C here. 0 XOR 0 is what? 0. It's giving us the value. When I take 7, 7 was giving us Z1 0 here. When I take 1 XOR 1, that one too is what? S0. So it means it's working. It's true. So there is the Z1 expression that you have for the gray code. Then now let's go and do Z2. It means the meeting has not yet ended. Then maybe we can end with this gray code thing. So Z22, let's draw the K map for it. We'll have this, and then AB here, CD here, 0, 0, 0, 1, 1, 1, and then 1, 0, 0, 0, 0, 1, 1, 1, and then 1, 0. Then with these two, let's fill. So in filling this, the first 4 bits are all zeros. They end here. So 0, 0, 0, 0, like that. Then the next 5 bits are actually ones. So the first 4 is 1, 1, 1, 1. And then the last bit being 1 here. Then the rest, let's represent them with donkeys to get more minimized expression. Now looking at this, we have a big problem because we can't put 4 by 3 together because you can't get 2 to the power n giving you 12, which is an integer, like in a way. So what then do we do? So what you do is this. You can group 4 at a time or 8 at a time. So what you can do is this. You don't have to use all the don't case to get the most simplified expression, right? But if you can use it to get the most minimized expression too, that would be cool. So what we can do is we can say that we are going to make use of all the donkeys we are having here so that we'll get this first 8 like this. And then we'll get the second 8 also like this. Now from the first 8, let me go back. From the first 8, Z2, from this first 8, we are having C and D all changing. They are changing from 0 to 1, 1 to 0 here and there. But then A is changing here. B is remaining as 1. So here is just B. And then or. Now let's do the second one. The second one is down here. Down here too. A is not changing, but B is changing. And A is remaining as high, which is A. So Z2 expression becomes A or B. So here too, let's take an example. Let's take 2 being 0 here. Let's go and look at 2 here. A and B. A or B, which is 0 or 0, gives us 0. Let's take 1, which will give us a 1. Let's take 3, for instance. 3 is let's take 4. 4 is a 1 here. So 4 here, you have 0 or 1. 0 or 1 is still what? A 1. So it's giving us the expression. Now, if you take any other one, you still end up getting the expression. So it means Z2 is just what? A or B, like this. Then we go and do for Z3. Then we are done. So for Z3 too, we will have this K map for it. A, B, C, D, 0, 0, 0, 1, 1, 1, and then 1, 0, 0, 0, 0, 1, 1, 1, and then 1, 0. So with these two, what we can get here is all the first 8 are all zeros. Like the first 8 bits are all zeros. So 0, 0, 0, 0. Here to 0, 0, 0, 0. And the last bit is 1. So 1 here. Then the rest are we are just going to represent them as donkeys. Now here, you have to think carefully because if I take, a donkey is here. If I take just these 4, I will get these 2 guys, which is A, B bar. But if I use all the donkeys here, I'll get a much more minimized version which is just A because B is changing from 1 to 0 here. So A. So whether I do A, B bar or A, I'll get the same answer. But then which one is the most minimum expression? Is A. So I'll just choose A as Z3, taking this whole 8. So Z3 is A. So that's Z3 is A. So when I check from 0 to 7 here, all of them had their A being 0. And then here too is 0 all throughout. When I get to B, it's just 1. So I just get a 1 here. That's all. So it's just A. A determines Z3, basically. So if you are to draw the output expressions for this gray code that we are seeing here, it would mean that you have this sort of thing. You have, let's say, A, B, C, D like this. Then I'll draw their lines like so. Then if I want to implement Z0, it's C XOR D. So I'll put an XOR here. Now say there's Z0. If I want to implement Z1, it's B XOR C. So I'll do this XOR C, this Z1. If I want to implement Z2, it's A or B. So A or B is this. A or B, sorry, Z2. And then Z3 is just A. So this Z3. So if I have this as 0, 0, 0, 0, all the way to 1, 0, 0, 0, I can use these expressions to get all the gray code representation of these binary digits. That's all allowed. Good that you are supposed to know. So this will be the answer that will be demanded from you. That's all. Please, is that clear? Okay. So yes, that's for gray code. Someone was saying RCD. Curtis, the RCD entails. The entails, please, what do you mean by the entails? Maybe we can do something small before 8. Then at 8 we just close. That's all. I'm listening now. I'm waiting for you. Someone was saying we can solve questions. So actually now you can do BCD to gray code and gray code to BCD with ease. So BCD to gray code and then gray code to BCD. Gray code to BCD is just looking at the expression that you have. What is it? So let's say I come here. I come here. This was a 0. So you just write 0, 0, 0, 0. This was a 1. You write 0, 0, 0, 1. This 3, right? So 0, 0, 1, 1. This 6. You write 6 here. This how do you call it? 4. Sorry, 1, 1, 0 is 6. This 2. This 5. Sorry, this 7. This 5. There's 4, and then there's 12. So in a way, that one, if they give you gray code, they tell you to change it to binary. You are just looking at what you are having there. So this is a 0. 0, 0, 0, 1 is a 1. 0, 0, 1, 1 is actually 3. 0, 0, 1, 0 is 2. So you write this in binary. Like that. This 6, this, that's this. But then they actually want you to change this to BCD. So in a way, arrange them like this. So it's this in the reverse direction to this instead. Yeah, if they put the question in that format. Yes. And then there is BCD to gray code. So gray code is just changing in 1 bit, that's all. Now, what is the RTD you were talking about? Can you give me the full meaning? Maybe I've forgotten my initials. RTD. RCD instead. Curtis, can you please tell me what the RCD is? And then you said things. I want to know which other things you were considering that we should do. Or you want me to touch on encoders too for you? I don't know what you wrote them on board. Okay, encoders. So let's use the 10 minutes for encoders. When it's 8, we are done. So for encoders, encoders is just about, someone is also saying something, I'm coming. Oh, what's, okay. So encoders is just about you trying to transmit something. You are trying to transmit something, but then it's like a bulk data. So the bulk data, you want to put them in something smaller than before. So it's like you are merging a lot of things together to be transmitted, basically. So that's an encoder. So encoding is, you have, let's say, 4 bits to transmit through a channel. But then you can actually use just 2 bits. Let's say, let me use 4 numbers instead. You have 4 numbers. 4 numbers to transmit. But you can use 2 bits to represent the 4 numbers. So why then not choose 2 bits, which is maybe X and X, which can represent 1, 2, 3, 4. So instead of sending 4 things like this, you send 1, you send 2, you send 3, and then you send 4. Why not send it using just 2 bits so that you reduce the energy, or if I should say the power you are using to send or transmit that signal. So in this case, since you have 4 things, you can use 0, 0, 0, 1, 1, 0, and then 1, 1 as the output, which is X, maybe X1, X0 as the output to represent these 4 guys. So that's the whole point of encoding. So it helps you reduce the amount of power, amount of energy that you are using to transmit the bits. So in encoders, we say that let your input, right, be say N. And then from this, we can say that N equals, and then let your output be M. So we can write N in terms of M as N being equal to 2 to the power M. So if you have 4, it means 4 in binary. If I want to solve for M, M is going to be what? 2, right? M is going to be 2. If I want 8, 2 to the power M, M is going to be what? 3 in that case. So it means instead of sending 8 different signals through the transmitter in a way, instead of sending 8 things like this, 8 of them, I'm now going to use just 3 things, X0, X1, X2, like this, to transmit all the 8, which will make things quite easier for me. So that's the whole point of encoding. So here, the most simplest encoder that you can have is a 2x1 encoder, because in that case, your input is 2. Then 2 to the power M means M is what? 1. So it means you can have this going to an encoder, giving you just one signal. So this X, this, let's say a 0 and then a 1. And then I can represent this as X, where X can be 0 or a 1, like this. If I have another case where I have 4:2, because so this is a 4:2 encoder, because 4 inputs, 2 outputs. So 2 to the power 2 gives us 4. So we are using this as the outputs. So I can have, let's say, I0, I1, I2, I3, like this. And then I can just use Y0, Y1 to represent it, basically. So if I have, let's say, 0, 1, 2, 3, can use 0, 0, 0, 1, 1, 1, sorry, and then 1, sorry, 1, 0, and then 1, 1 to represent them. So instead of sending 4 different things, 0, sending 1, sending 2, sending 3, I can just use 2 signals, which can be 0, 0 at a time when this 0 is enabled. So it means we can only transmit 1 at a time in this case. So it can be 0, 0 at the output. If 1 is enabled, it could be 0, 1. If 2 is enabled, it could be 1, 0. If 3 is enabled, then you have what? 1, 1 being transmitted through your channel. That's all. So that's the whole point of encoding. And then decoding is the reverse. So you wanted to send 1, but in the transmission line, you were using, let's say, 0, 1 for it. Since maybe you were having 4 different things, you wanted to use 2 base to transmit it, X0, X1. So if you want to decode it, you use this small tool to come and get the 4 different things like that. So if you enable 0, 0 to come out, then it's, sorry, 0, 0, then it's a 0. If you enable 0, 1, it's a 1. If you enable 1, 0, it's a 2. If you enable 1, 1, it's a what? A 3. That's the point of decoding. So you send using smaller energy, and then you decode it to get your actual message back. That's the whole point. So it's technically used in data transmission, the encoders and then the decoders. So this is just a small overview of the encoder. We can actually go to your slides to check some of the things he was doing. So let's do this shortly. Let me go through this with you. So here you have D0, D1, D2, D3 as 4 inputs. So your input is 4. And then 2 to the power m, there's your output. So your output should be what? 2, because 2 to the power 2 gives us what? 4. So it's a 4:2 decoder, sorry, encoder. So here, your 4 inputs, right? It could be zeros, or it could be, let me say, it ranges from 0 to 3 in a way. So if your output is 0, 0, then D0, which is 0 is here, 1 is here, 2 is here, 3 is here. If, let me use my whiteboard so that you see this clearly, because we have 3 minutes. Hey, 1 minute. Please pardon me. Let's use this example to understand this. And then D0, have Y1 and then Y0. Let's see how we fill this table. So if here is 0, 0, because we can have 4 possibilities, 0, 1, 1, 0, and then 1, 1. In that case, we can have just 4. Now this 4, what are we getting? Because here is a 0, here is a 1, here is a 2, here is a 3. So if it's 0, 0, D0 should be high, which is the 0 as the input. So D0 should be high. All the rest should be what? Zeros. That's the whole implementation here. if it's a 0, 1, if the output here is 0, 1, 0, 1 is for D2 here. So it means D1 should be a high. All the rest should be zeros like this. Now, if the output is 1, 0, 1, 0 is 2. This one, 2. That goes with D2. So only D2 should be high. So you come here, you put a 1 here. All the rest should be zeros. So it's like connected to ground and connected to VDD, like high voltage. Then if you have 1, 1 at the outputs like this, 1, 1, then 1, 1 is 3 in decimal, which is D3. So it means D3 should only be high. The rest should be grounded in a way. So this is the logical table that you have. And then you implement D0 as a normal 0, which is, here you want the Y0 and then the Y1. So if you want Y0, you check from here. Y0, where is the 1? Here and then here. 1 here, there is only D1, right? So D1, all the rest are zeros. So you can bar all of them, which is not really needed if you are using a simplified SOP. Or you can have D3 here, giving you a high at Y0. The rest all will be bad. It's not really needed. Then if you want Y1 too, Y1 is a high here and a high here. What is giving you that high? D2 and then D3. So it means you have D2 or D3 as your Y1. So that's the implementation of an encoder. So basically, it's like seeing it as if you want a 0, 0, there are 4 inputs. Only this is 0, 1, 2, 3. Only this one is connected to VDD, like this, VDD. The rest are all grounded. That's all. So in this case, if you pass it through the encoder, 4x2 encoder, you get 0, 0 coming out of your circuits, because that's the only high. The rest are all grounded. That's all. So that's just some brief explanation of the encoders. If you are supposed to draw, then you just place D1 and D2. You take them through an OR gate, then you get Y0. You do same for D2 and then D3. Then you get your expression for Y0 and Y1 respectively. That's all. So we can actually end the class here. Thank you for joining. I don't know if we can meet another time. I'm not so sure, but maybe. But we'll end here for now. I think we've spent a lot of time here. Yeah. So actually, you can use the same analogy we've used for the normal one, which is the 4x2 encoder for the rest of them. So you can go through it like religiously. You just know that if you have 8 bits, it's going to be 0 all the way to 7. And then you are going to use 3 outputs for it, right? 8x3. So the 3 is going to run from 0, 0, 0 all the way to 1, 1, 1, which is the 7. So if you are getting 0, 0, 0, then only 0 should be a high to be sent to the outputs. So 1 at a time. The rest should be all zeros. That's all. If it's a 1, which is 0, 0, 1, only D1 should be a high. The rest all should be zeros. That's all. That's all about the encoders. And then the decoders are just the opposite of these encoders we've looked at. Yeah, so that's that. So thank you for joining. Think we can end the class here. I'll see you some other time.